Welcome. In this video, I'll be solving simple annuity problems in Excel. An annuity involves equal payments made at equal time intervals. In simple annuities, payments per year and compounding frequency per year are equal. That is, if payments are made quarterly, then interest is also compounded quarterly and vice versa. We begin by calculating the future value of $3,000 invested each year at 8.4% compounded annually. For years we have 15. Payment and compounding are annual, so PY and CY are 1. The nominal interest rate or APR is 8.4% or 0.084. In the Excel formula for future value here, rate is the periodic rate. So in simple annuities, to compute periodic rate, we divide the nominal rate by the compounding frequency per year. NPER is the number of payments in the annuities, not the number of compounding periods. It is obtained by years times PY. The periodic payment here is 3,000. There is no present value, so we enter 0. To compute the future value, type equals FV, tab, rate, comma, number of periods, comma, payment. I'm going to make that negative so the future value can show up as positive, comma, then present value. For type here, you can ignore it or enter 0 if payments are made at the end of the period. That is ordinary annuity. However, if payments are made at the beginning of the periods, that is annuity due, you must enter 1 for type. So I'm going to input 0 since payments are made at the end of each year here, and enter. And here is the future value of those payments. Now let's compute the future value assuming the payments are made at the beginning of each year by inputting 1 for type. You can see here that the future value is larger when the payments are made at the beginning of the year rather than at the end. This is because the cash flows are compounded for one additional period when payments are made at the beginning. In essence, the first payment in an annuity due would already be accruing interest by the time the first payment in an ordinary annuity is made. Now, the total paid here will be the periodic payment times the number of payments. And the interest earned will be the future value minus total amount paid. Next, we compute the present value of a simple annuity. How much was borrowed at 7.89% compounded quarterly if paid off with $12.88 every 3 months for 9 1/4 years? For the 9 1/4 year, we can type equals 9 plus 1/4. Enter. Payments are made every 3 months, that is quarterly. Interest is also compounded quarterly, so PY and CY are both 4. The nominal interest rate is 7.89% or 0.0789. Again, since this is simple annuity, the periodic rate is the nominal rate divided by the frequency of conversion. NPER is the number of payments, which is years times PY. Periodic payment is $12.88. The loan will be paid off at the end, so future value is 0. To compute the present value, type equals PV, tab to select, rate, comma, number of periods, comma, periodic payment, comma, future value, comma. Now I'm going to assume payments are made at the end of time period, so I'll enter 0. Enter. And this is the amount borrowed. It shows up as negative since I entered payment as positive. To make it positive, I'll double-click the cell and make the payment negative. Now let's see what the present value will be if the payments were made at the beginning of the period. I'm going to input 1 for type here for begin mode. You can see that the present value is higher in begin mode. This means we can borrow a little more with the same periodic repayment amount if we pay at the beginning of the periods rather than at the end. The total amount paid is periodic payment times the number of payments. The interest paid on the loan will be the total repayment amount minus the amount borrowed. Next, we compute the periodic payment, PMT. Here we want to determine the monthly payment that will reduce a $17,000 loan to $5,000 at 6.59% compounded monthly over 6 years. Years here will be 6. Payments are made monthly and compounding is monthly as well, so PY and CY will be 12. The nominal interest rate is 6.59% or 0.0659. The periodic rate will be the nominal rate divided by 12. The total number of payments will be years times payments per year. We have a loan of $17,000 at the start, so that will be our present value. Typically, when paying off a loan, our future value should be 0. But in this case, we want to reduce the loan to $5,000, so $5,000 will be our future value. To compute payments, type equals PMT, tab, rate, comma, number of payments, comma, present value, comma, and future value. I can hit enter here because type is optional if payments are made at the end of each period. But I can also enter 0 for type to indicate that. Enter. Now there is a problem with this payment amount. The problem lies in the fact that both present value and the future value are positive in the input. That indicates that if we borrow $17,000 and repay $343.3 every month for 6 years, at this interest rate, we will end up having a positive balance of $5,000 in the account. Since we're only interested in reducing the loan to $5,000, we need to make one of present value and future value negative. I'm going to make the present value negative here. Enter. And we have the correct payment amount. Now, suppose these payments were made at the beginning. I'm going to copy the payment formula from the formula bar and change the type to 1 for begin mode. And here we have a slightly lower periodic repayment amount if payments were made at the beginning of each period. Finally, we compute the number of payments in simple annuity. How long will it take to repay a $78,000 loan with monthly payments of $1,500 if interest is 10.39% compounded monthly? Since payment and compounding are monthly, PY and CY will be 12. The nominal interest rate is 10.39% or 0.1039. Since this is simple annuity, that is PY equals CY, the periodic rate will be the nominal interest rate divided by the compounding frequency per year. The periodic payment is $1,500. The present value is the amount of the loan, which is $78,000. The future value will be 0 since the loan will be fully repaid. To calculate the number of payments, type equals N per, rate, comma, payment, comma, present value, comma, and future value. Since type is optional, I can hit enter. It gives a negative number, which means something went wrong. The number of payments cannot be negative. The reason for this negative number is because both payments and present value were entered as positive values in the formula. This is incorrect as they should be moving in opposite direction. One of them must be negative. So if I make payment negative, we see that it gives the correct number of payments. This 69.4 payments indicates that there will be 70 payments in total. Since the payments are made monthly, it will take 70 months or 5 years and 10 months to fully repay the loan. The first 69 payments will be the full $1,500, while the 70th payment will be a partial payment, less than $1,500. Note that the last payment is not going to be exactly 0.4 times $1,500, but it will be close. To determine the actual size of the final payment, you can compute the future value of the 69 payments as shown here. Now, suppose these payments were made at the beginning of each period. I will copy the N per formula from the formula bar, paste here, and add type equal to 1 for begin mode. You can see here that the number of payments for begin mode is 1 less than the number of payments for end mode. In essence, the loan will be paid off 1 month faster if the payments have been made at the beginning of the periods rather than at the end. And that's it for this video. Thanks for watching.